Hey, I want to talk about single line diagrams, block diagrams, and risers. There's some question as to why you use one or the other, what the difference is, and like what kind of information goes into each specific thing. So I'm just going to go over a couple example diagrams and show you what to put on them and what to look for and what they're used for. So let's just get right into it. Alright, so I have a couple single line diagrams to start off with. And single line diagrams are a simple representation of an electrical distribution system using a single line to identify the feeder from a source to a load. So hence why they're called single lines. They're also called one lines. Some people call them one line, single line, or stuff like that. So that's what this is. So we have here a double-ended substation. And, well, technically switchgear. There's no transformer. We have a double-ended switchgear, and we have our loads coming in. So there's some things that you can see on a single line diagram, such as like where to reference for the extension of this diagram. So like here, for example, you can see that for normal power, we're referring to a different drawing for a different substation. And then it tells you what type of feeder comes in. So this is an underground duct bank. Other things that you can see off of a single line diagram are items such as SPD, surge protection devices. So this is a lightning arrestor, so that's why LA. And it comes into some metering, so facility meter. And there's breakers, so this is your main breaker. And other things you can tell just from the way things are drawn. For example, this breaker has these little triangles, so they're called stabs. And essentially what that means is that it's a draw out breaker. That means it's a big compartment that you can crank, the whole thing out. So you can draw this breaker out of the unit. So that's what that means. It's a draw out breaker. If you were to go down to something like this, for example, these are bolt-on breakers. You see that they don't have those stabs like the other ones. So this honestly might be a mistake. These these might be bolt-on breakers. But yeah, so most of the loads that are serving from a switchgear tend to be draw-out breakers. And then when you get down to a switchboard, which is on a different drawing, a switchboard tends to have bolt-on breakers. So some important information that you can get off of the equipment are the location, the name, and then you'll be able to put notes on a single line diagram, which is better than a panel schedule. So if you were to just make a panel schedule for a switchgear, you'd be missing a ton of information. So for example, this is the bus, and it tells you how many amperage, what the voltage, how many phases, how many wires, and this sometimes says bus A or bus B. So like you can split a main tie main switchgear in half, and like this is side A and this is side B. That way people know like where the feeder runs to. The exact number of breakers and spaces and spares is exactly what's ordered. So you see here that we have seven breakers and a space. That's exactly what gets ordered on the submittal when it comes in. So the breakers themselves also have more information than a panel schedule. So here we have the frame size specified. So 2000 amp frame, 2000 amp trip, and this is a electronic trip. So there's like a unit in the breaker that you can trip it at different settings. So like for example, here the main breaker, it's a 6000 amp frame, but you can trip it at 5400 amp. And then you can see there's other information that's relevant to this breaker. So for example, this is LSIG, long, short, instantaneous, and ground. So that's like a special feature of the breaker. It also tells you if you want 100% rated or series rated. And then this is electronically operated and normally closed. So like here you can see we actually have 4 breakers in this whole setup right here. So we have 2 mains that are normally closed. And then we actually have 2 ties. Actually, one of these tends to be closed. But anyways, this tells you normally open, normally open, normally open. And then these main breakers are normally closed. So under normal circumstances, this switchgear will operate in half. Like the left half and the right half, they're not tied together. But if for some reason you lose this feed coming in, you can open this breaker and then close these ties, and then this source right here will pick up the whole switchgear. So that's a lot of good information that you can put on a single line diagram that you typically wouldn't show on a panel schedule or even a riser diagram or a block diagram. So we'll get to those later. The riser diagram and block diagram are simplified versions of this type of drawing, and you want to show different types of information in those. So a single line diagram has a lot of small granular details. So you can see here that we have a whole bunch of notes. So sheet note 1, basis of design, tells you exactly what we had in mind when designing the switchgear. So notes 2 and 3, they could have operation notes. We even have like the normal standby generator switching, which ones to shut off and which ones to switch over in what order. There's, let's see, there are feeders to some transfer panels, essentially. That's essentially what this is. So there's certain things that you can say on a single line diagram, such as key interlocked, and that means that only one of these breakers can open at one time. One stays open, the other one's closed. So again, you can see here, normally closed, normally open. So the continuation symbol is important to pay attention to. There's multiple ways to do this. I've seen it where the tag on this end versus what you see on the other end. So let's see if we can find an example. So here we see 1. So this is sequential, 1, 3, 5, 7, and then the other side is even. So 2, 4, 6, 8. But for example, this one, number 1, the first feeder of this switchgear goes to life safety 1 ATS1. So if we go down here to life safety 1 ATS1. So here it is. So this feeder continues and picks up here. So you see that this is identical to the one up here, right here. Some people do it backwards. So like up here it would say 1, and then this would say the source end, or the load end. So like this would actually say LS1 ATS1. There's multiple ways I've seen it done. As long as you're consistent, I guess you could follow along, but this is what we happen to do on this project. So you match this symbol at LS1 ATS1. See this drawing. So we'll go down here, and here it is, 1 NP1 MD SWG1. So that's the same symbol. So that means that it comes through here and it feeds this ATS. So you'll see a lot of that on a single line diagram where they'll send the power to a reference, and then the other reference picks up from another drawing. So just make sure that that's consistent if you're drawing it, and ask your engineer on record or your company QA person, like, what's the standard? So figure that out and you'll end up using that a lot. Let me jump to another diagram. The other reason that I like to use single line diagram for like mechanical equipment or process equipment is because we need to specify disconnects, VFDs, and other transformers and things that are hard to specify in a panel schedule. So if we drill into this distribution panel right here, you can see that this is drawn like the switchgear. You have your source come in. This one doesn't have a main breaker, but we have your surge protection device, your bus, and then your breakers feeding mechanical load. So here we can specify that a VFD is to be provided before you get to the motor. And here we also specify the different types of conductors. And note 7, pretty sure, specify that this is a VFD cable. So like you can put a lot of information for the contractor to bid and build off of on a single line diagram. So if we jump down here to, for example, this one here, you can specify a transformer after the breaker, and then this is your panel board. So like once you get to this level of detail, this is like a branch panel. So everything after that is just single pole to a receptacle or to a light switch or something. So like from here on down, you could just show a panel schedule. You don't have to show a single line diagram for everything. So the diagram usually stops at a point where it's simple enough that we don't need to specify all of this stuff here. So let's just jump over to, single line number 3. This is kind of an extreme case. We have, this is mechanical. This is all mechanical. So we have air handlers out the wazoo here. So from here, it just goes on and on and on, and it specifies exactly which VFD. We have the tag for the VFD and what air handler it goes to. So that's like the huge reason that we would use a single line diagram. This happens to be just a distribution panel, but you would single line motor control centers, switchboards, substations, switch gears, like the big stuff that you want to specify all the little intricate details of that equipment. So draw a single line diagram for that. Just cleanliness wise, you'll notice that we like to keep everything evenly spaced. So I can already see right here, this space for some reason is bigger than this space. Keep it consistent. Like if it's 1 3/4, do 1 3/4 all the way down. And everything should line up. So like this is our feeder tag. I don't know why it's up here and not like right here. Like it should be centered on centered. So whatever the space difference between that, center here, space difference, center there. Just make it look nice and don't be all hodgy-podgy. Like sometimes it's this stuff like here, line it up when you can. If you absolutely can't, then okay, at least this is consistent. So I can take this. This is not bad. Other things is just, you see how there's different colors to everything. So if you look at layer, you can see that we have all the buses on yellow, equipment is cyan, feeder size, you get the idea. Put everything on the correct layer so that it's just more organized. And if you have everything just like the same color, it's actually hard to even read. So like imagine this looking like this. Like that's not the easiest thing to decipher, right? Granted, when you PDF it, it's all black and white anyways, but if you're working in CAD, take advantage of the colors, right? So we're just gonna undo that. So that's my third example. I think my fourth example, oh, I don't have layers set up. Okay, everything's the same color. All right, here, let me show you a trick. So if you want to bring all your layers from one drawing to the other, go into your layers. Oh, this is already set up. Well, anyways, go into your layers and you can do new and you can say export to new CAD or something like that. Hit OK and then close that, hit save, and then go over to your new diagram. So from here, you go into layers as well, or layer. Yeah, you go into layer and then, nope, I said it wrong. You go to layers with an S. There we go. So here we want to import this. So import from diagram 3, and let's do the top one. Sure, that's the one I just made. So import that, click on it, and then hit restore. So there we go. We just brought all of our layer colors over. Yeah, that's a little easier. Okay, so this is just continuation. You see how everything comes in from like the switchboard or the switchgear. So that's how you reference things. So you go to drawing E5005, find NSP1 switchgear 1, and look for tag number 5. So that's where you can figure out the breaker that is connected to upstream. So same thing here. You have your You have your distribution panels detailed out. We have our location, our switch size, our fuse size, clean room fixture, and it specifies the equipment that you are connected to. Same thing, keep going down. Yeah, all the same stuff. All right, let's jump over to a riser diagram. So a riser diagram is different in that it shows the elevation of the building. So it's like, imagine it rising up the building. So that's where the name comes from. Over here, we have an example riser diagram from a different project. And you can see here that we have such designation as basement, first floor, second floor, third floor, and penthouse. So this is a bit more detailed in that it resembles a little bit of a single line diagram in this riser diagram, but essentially we wanted to show this vertical busway. So this is a 1000 amp 208 123 phase 4-wire plug-in bus duct, or bus duct busway, same thing. And there you can show this running vertically, and we have it designed such that we have bus plugs in here going to panels and distribution boards. So from here you can see that the first floor has 2 distribution boards, and we have 2 branch panels out of each distribution board. This one has 4. So similar features here. So like from here on, from here on down looks like a single line diagram. But if you were to keep going up, you'll see that each floor has more and more information with the floor indicated. So a riser diagram can be simpler than that. Like, you don't have to draw out the distribution board. If you really wanted to, you could, I guess, blank this out and then have your single line separate. So like your riser diagram would literally just be, you know, a tap off of your busway to a distribution, and then you'd have your branch panels beneath that. And then you can reference to a single line for more information. For this project, it just made sense to put it on here. So we put all the information such as the panel name, where it is, this note SL3, wherever it is. SL3 calls for NQ type panel board and NEMA 1 enclosure. So it's like a basis of a design. I spec'd Square D, I guess, for this one. So that's the kind of information I put here. You have your 22,000 AIC available in Rush Current, so that way when they order it, they can have the appropriate short circuit current rating. So like this is, if you had, I believe it's like a 3-phase fault or something, the amount of current that can pass through at a given time. So the higher that is, the more robust your panel board and breakers have to be so that it doesn't explode. So like if you had 65,000 AIC at this location, but you only spec'd a panel board that is up to 22,000 and you had a big short inside the panel board, you could literally have your breakers explode and it could kill someone. So that's important information to put on here. So you have your AIC information up here, you have your bus size and all that good stuff down here. Then you can specify your breakers, and for some reason we didn't have spare breakers on this distribution panel. I always put spares and spaces whenever I can. But that's your riser diagram. So from here we can go even simpler, and that's what the block diagram is for. So a block diagram looks like this, and what's with our layers, man? I hate looking at something that's all the same color. All right, well, not worth it. For this case, a block diagram has a little bit of a riser flavor to this. You can see that we have first, second, third, and fourth, but we also have some room. So you can see like this is blocked outside. So grade is up here at second level. So this is on grade. We have a red line dividing utility versus client-owned equipment. And then all this stuff comes underground to our main electrical room. So the main electrical room has a more detailed block diagram, and it picks up where this drops off. So this tells you, like, in room 1408, we have this distribution panel. And then you can kind of see that this is a stack. So we have like a 4 electrical closets stacked on top of each other in one spot. So that way we can have like a vertical feeder that just runs through everything and it just picks up all these panels. This stack over here is over the main electrical room. So, you know, gives you a little bit of an idea of how the whole system is arranged. And then we have these random spaces that are kind of like out in the west side of the building. We couldn't really stack them, so that's just where it is. So the detail level for this is that you just reference. So like here references this block diagram, and it says like it goes to, I don't know, this one here has 2 feeders. So 2 feeders coming from the switchgear 3 and switchgear 4 going to this distribution panel 1. And then, you know, it just keeps feeding down. So a block diagram is easy for someone that's not electrically savvy to follow along a little bit better. Like out here, you can see we have 2 utility services coming in. We have a distribution switchgear out there, and there's 3 substations. One of these substations is dedicated to the fire pump. I mean, that's pretty easy for someone to follow along. Looks like we have some voltages listed. So like, you know, from here, you can see that our generators are 480, 277. I think we left out sizing. Yeah, like here we don't bother saying the size because it's already stated on the single line diagram. But you can see that they're located outside. They feed underground into the main electrical room. So there's really good areas for, ooh, wow, that was a big note. There's really good scenarios where you would use a single line diagram or a riser diagram or a block diagram. So there's like all these different flavors of diagrams that you can use, and it just takes time to get to know them all. But once you get to use them a couple times, you'll understand, like, if someone asks you for a distribution for a panel board, you know that you draw a single line diagram. The panel board itself, just give them a panel schedule. And if they want to know where it is, give them a riser diagram. All right, hopefully that wasn't too confusing. Please ask questions if you want more in-depth review of, like, just the riser diagram or something. If there's any discussions to be had, go check us out on Discord. And if you want to draw this up in Revit, check out this video here. I'm probably more fluent in CAD, so maybe I'll make a video on that. Okay, thanks for watching. I'll see you guys next time.